In this video, we'll look at hybridization of our electron orbitals. When we think about bonding and our orbitals, we know that a covalent bond has the orbitals overlapping. If I look at hydrogen, I would take a 1s and another 1s, and they'll overlap and the electrons will be shared in the middle here. That's how we form a covalent bond. Or another example, if we look at HCl, I'd have the chlorine's 3p overlapping with the hydrogen's 1s, our covalent bond. And the overlap here would create our covalent bond. Or we can think about if we have two chlorines, they'll both be using their 3p and overlapping the 3p orbital to create a covalent bond. But all of these, we have this orbital overlapping, and it doesn't matter which type of orbitals are overlapping as long as there's some. Some orbital overlap gives us our covalent bond. But now that we've looked at Lewis structures and our three-dimensional structures, let me ask you all a question. Why does carbon make 4 bonds? Why did we draw carbon making 4 bonds? If we look at the orbital diagram, I have a 2s2 and a 2p2. How can I get 4 bonds out of this? I have an empty 2p orbital and then missing 1 electron from each of these. Now we said if a covalent bond, the electrons are sharing so that they can pair up the electrons. Wouldn't I only be able to make 2 bonds here? Why can I make 4? Why did we draw carbon with 4 bonds when here it should only make 2 if we look at the orbital diagram? Even if we add a small amount of energy, I can excite the electron from the 2s into the 2p. At least here now, I have 4 unpaired electrons, so now I can make 4 bonds, right? Right. The carbon is going to share each one of these valence electrons and make a bond. Now, 3 of them are in the 2p, so 3 of them should have the same energy. But that 2s, it's a different energy level. So that means if carbon made 4 bonds like this by exciting 1 electron from the 2s up to the 2p, I should see a difference in energy between this 2s and 3 bonds from the 2p. But when we look at carbon, there isn't any energy difference. All the bonds are the exact same. This diagram wouldn't work then. The electrons are in different energy levels from the 2s to the 2p. So how can I make 4 bonds that are the exact same energy? The answer? Hybrid orbitals. If I take the energy of the 2s and the 2p and I mix them together, I can create a hybrid orbital. And so if we think about our configuration, I had the 2s and the 2p. They each had 1 electron. If I take these 4 orbitals, mix their energies, put them in a blender, create new orbitals, I can end up with what we call an sp3, because I took 1 s orbital and 3 p orbitals. See? 1 s and 3 of the p orbitals. If I took 4 regular orbitals, put them in my blender, mixed them up, created a hybrid, now I have 4 hybrid orbitals. So however many orbitals you start with is the amount of orbitals you end with. And now with my hybrid orbitals, they're all the same. They all have the same energy level. They're all degenerate. So now when I make a bond with these hybrid orbitals, all the bonds will be the exact same as each other. And so if we looked at our orbital diagram with our energy, A 2s would be down here. Our 2p might be up here. So if we mix those two energies, it'll end up somewhere in the middle here. So if my 2s is lower in energy, but my 2p's are higher in energy, mixing those two together, I'll get a hybrid orbital that's a little bit lower than the 2p, but a little bit higher than the 2s. But doing the hybrid orbital this way, now I can make 4 bonds that are all the exact same as each other. And so now let's look at these different hybrid orbitals. The first one we'll look at is sp orbital. The sp hybrid orbital, as the name implies, I'm going to mix one s orbital and one p orbital, which gives me 2 hybrid sp orbitals. And they'll arrange themselves as far apart as they can get from each other. So they'll arrange themselves on opposite sides. So here, when we draw a p orbital, this is one p orbital made the 2 lobes on each side. Here, this is 2 different orbitals. So now I have 2 different orbitals that I can make bonds with. And the 2 different orbitals are on the exact opposite of each other. They're 180 degrees apart. So that's how when we looked at the Vesper theory and we looked at, Vesper theory and we looked at the 3-dimensional shapes of our molecules, anything with 3 atoms ended up being linear, no matter which orbital we used. And this is why it actually uses a hybrid orbital. But you can see when we're looking at the individual hybrid orbitals, I have one large lobe and then one small one. And the large lobe is slightly more rounded than a regular p orbital. So you can see it kind of looks like I mixed an s and a p orbital together here. It became more rounded that we got from the s orbital, but it had the 2 lobes like a p orbital. So you can think of your hybrid orbitals as almost the children of the 2 different original orbitals. And if we were to draw an orbital diagram for an sp hybrid, it would look something like this. I'd have a 1s, and 2 sps, and then a 2p. So I'd have 1 box for my 1s, 2 boxes for my sp because I took 1 p and 1 s, and then 2 boxes for the p's, the unhybridized p orbital. So this means when we have a molecule that's sp hybridized, it has 2 hybrid orbitals and 2 unhybridized p orbitals. And so we can make our single bonds using the hybrid orbitals. So when we make a covalent single bond, that uses a hybrid orbital. The unhybridized are used for other stuff, but the hybridized orbital is used for single bonds. And so an example, if we look at beryllium difluoride, we know is linear, 180 degrees apart. And this is how the atoms are actually bonded together. The beryllium is using its 2 hybrid orbitals to get 180 degrees apart to create its linear configuration. So that beryllium is an sp hybridized atom. Now let's look at sp2. So sp2 is when I take 1 s orbital and 2 of the p orbitals, hybridize them together, create an sp2. So the original electron diagram would have looked something like this. So with my original diagram, or our unhybridized diagram is a better way to say it, I have our 1s, our 2s and then a 2p. So if we look at what happens, I'm going to take this 2s and two of these 2p's, hybridize them together to create that, to create my sp2. And this left me with an empty 2p orbital here, which now shows up here. And since I had 3 electrons in the boxes that I circled, I have 3 electrons up here. So I have 3 electrons in my hybridized orbital. So you can see however many boxes we circle, we end up with that many hybridized orbitals. And if the electrons are in those boxes, they come along, they end up in the hybridized orbitals. So in an sp2, my orbitals are all bonded at 120 degrees apart from each other. This is how we get our 120-degree angle for trigonal planar molecules. So you can see here I have one of my sp2 orbitals, a second one, and a third one. And they end up with a trigonal planar configuration. Now the sp2, the lobe is actually a little bit larger than just the sp. So it looks a little more like a p orbital than our sp orbitals did. sp2s are a little more p-shape in p configuration because I used 2 p orbitals. I used 2 of the p orbitals instead of just 1, and I still only have 1 s orbital. So you can think it got 33% of its character from the s orbital, and then 67% from the p orbitals. So it's 67% p orbital-like and 33% s orbital-like. So now let's look at the next one, sp3. The same idea that we saw when we looked at the carbon here. If I took an s orbital and all 3 of those p orbitals, hybridize them together, that's how you get a tetrahedral shape. So it's the hybridized orbitals are really what gave us the shapes of our molecules. And since I've taken 1 s orbital and 3 of the p's, I now have 25% s orbital characteristics and then 75% p orbital. So you can see this would look even more p orbital shape versus my sp or my sp2. Now let's look at our expanded octets. So with our expanded octet, we're not only taking the s and the p, we're also taking the d orbitals. So if I take an s orbital, all 3 of my p's, and a d orbital, hybridize them all together, so put them in my blender and mix them all together, I get an sp3d, which is how we have our trigonal bipyramidal shape. And so you can see if I took 1, 2, 3, 4, 5 different orbitals. Now I have 1, 2, 3, 4, 5 different lobes. There's our shape. There's our hybrid orbitals. And then finally, with our sp3d2, this is how we get octahedral. I take my s orbital, all 3 of the p's, and 2 d orbitals. Hybridize them together, you get sp3d2, and then we still have 3 empty d orbitals because I still had 3 boxes here. So I end up with 3 empty 5d orbitals. But all the rest of here, all 6 of these, hybridize together to create sp3d2. That's how we can end up with octahedral. And even though we're mixing 3 different types of orbitals, we still end up with the same bond length and bond energy across all these different atoms and all these different orbitals. So here, if we summarize our different geometries and our hybridizations that go along with those geometries. So we can think the hybridization tells us the electron group geometry. So if I take two hybrid orbitals, I end up with a linear, or I can say it's sp. If I take three orbitals, I end up with sp2, which is trigonal planar. Four orbitals, when they get hybridized, I get sp3 and a tetrahedral shape. Five orbitals, when they hybridize, you get an sp3d and a trigonal bipyramidal shape. Six orbitals, when they hybridize, you get an sp3d2 and an octahedral shape. So this is how we get our electron group shape. And from this, then you can figure out the molecular shape, right? But this is how we get the electron group shape, is we look at the hybrid orbitals. So now you guys should be able to figure out the hybridization of the different orbitals and how to draw the orbital diagram for it.